Well, you can start messing with the clutter, like what stuff is reflected to you that's off of the ground by varying basically the velocity vectors for the transmitter and receiver, since you control those. So there's some cool stuff that kind of comes out in the fancy case. All right, no radar talk is complete without the radar equation. So basically, the thing on the left is how much power is reflected back. And then the P sub T is how much power is being transmitted. And then that big G is kind of the gain of my transmitter antenna. It's how, basically how big or directional it is. That A sub R is really the corresponding answer for the receive antenna. They just draw it a different way. Sigma is what they call the radar cross-section of the target. So a bigger, and it's got units of square meters. So the bigger the target it is, the more power gets reflected back, which makes sense. You got a huge object, easier to see, 757 than to see some little Cessna or something. And then those are the two path lengths. Where this comes into play is you're trying to figure out how good the RF performance, the radio performance needs to be, and kind of how does this perform in a noisy environment. And also, since the farther away everything is, you get this like 1 over R squared basically loss. So the return signal falls off pretty badly. Okay, so now passive radar is the one we're interested in, and it's a subclass of bistatic radar. So the math turns out to work out pretty much the same way, except in this case, we don't own the transmitter. So we're going to use somebody else's transmitter. And this has got all kinds of great advantages. The starting with which is we don't have to run the transmitter, we don't have to pay for the transmitter. You look at radar transmitters, often they're like running at a megawatt. They require, very fancy, hard to get license. I'm certainly not going to pay the power bill on the megawatt transmitter, or, excuse me, I need this big chunk of land, and, don't walk near me when I'm blasting away here. So we look at, it's pretty interesting. You look at, there are some passive radar systems. There's one at the Haystack Observatory at MIT, and they have this giant dish. They got 2 of them, actually, one of which just points straight up. It's not steerable, just points straight up. And then they got one that steers. But they use it for doing, mostly they're looking at stuff in the ionosphere. It runs at about 400 megahertz. And they also have observed that they see all the low Earth orbiting satellites. It's like, okay, good. So we look at all right, transmitters, what do we got? All right, we can get, there's a bunch, all right. That's kind of like there's cellular up there, there's public safety, there's microwave point-to-point. It turns out there's actually no FM transmitters up there, no broadcast FM. That's a megawatt television transmitter. There's another on the order of megawatt television transmitter. They're all over the place, okay? So the question is, okay, well, who are we going to use? So we find somebody's transmitter, then we need to either have multiple coherent receivers. And what we mean by coherent is that, because we're listening to two signals, we might have one antenna is pointed directly at the transmitter, and maybe another one is pointed sort of away from the transmitter, or maybe we're building this phased array where we have a bunch of antennas. The trick is that we need to be able to do, when we're doing sampling, and when we're doing the down conversion of the RF signal to baseband, where we're going to sample it, all that needs to be in lockstep. So there's this tricky thing about, if you took two radios, mostly radios don't come where they can all be exactly synchronized. So this is kind of a piece of the problem. So, watch the reflections, do the math, and figure out where it is. How hard could it be? Okay. Don't you love the problems that have, this is one of those problems, a real simple description. Okay, so we say, all right, well, what are we going to use? And again, the thing is, we don't control the signal out of the transmitter. So we don't get to say what they're transmitting in the traditional radar system. The guy on the receive end knows exactly what the transmitter is transmitting. They either know kind of a priori, like they know if it's a spread spectrum transmitter, they know exactly the spreading code they're using. But in our case, we can know just because we know the class of signals it's transmitting. We have some information about it. So broadcast FM, this is about 100 kilohertz wide. It's probably the easiest one to do. Analog or digital TV. This is actually probably the more interesting one as far as the kind of how fine of resolution you can get, and we'll talk about that in a little bit. And then there's an outfit in the UK called Roke Manor who claims to be doing GSM-based, they're calling it CELDAR. where they use GSM base stations as the transmitters and they watch the reflections. From my reading of their literature and talking to some other people, we're not really clear how useful it is because the base stations are relatively low power, so you don't see anything until it's right on top of you. So that's kind of like, unless they're looking at vehicle traffic or something like that. But aircraft, they're on your head before you notice them. I don't know of anybody who's actually done UMTS, but it has the advantage of being quite wide bandwidth, which allows you to do a more precise fix on the location. Other choices, actually, these have all been tried too. High-powered satellites, the DBS. I know that people have tried this with military satellites which aren't this high a power, so this might work. I know of people who have done it and made it work with GPS satellites. And so they have the satellite as the transmitter, and then they're flying an airplane as the receiver, and they tell me they're watching, weather or waves on the ocean. I think they're looking for ships, but again, the cool thing about the GPS stuff, the satellites aren't that powerful, but they do cover everything. And it's a spread spectrum thing, so you have this big coding gain. So you can basically correlate stuff and go find the weak reflections. And then another trick that's been done really all the way back to World War II was you take advantage of other people's radar transmitters. Sometimes they're a friendly transmitter, and they could be a hostile transmitter in a kind of a military situation. But again, they're high-powered, they're transmitting, and as long as you can point at them and you can get to see the reflections back, you get to take advantage of that. The secondary surveillance radar system, this is like the Squawk ID, that, like at the air traffic control, they like to know just not where it is, but they like to know like altitude reporting and all this. So there's a secondary thing that pulses out at the airplane, and when it sees it, it has its own transmitter that sends some encoded information. That stuff's about 1.9 gigahertz. Okay, so before we headed down this path, we said, are we totally crazy, or has anybody else done this? So the top one here, the Lockheed Silent Sentry, is in the money is no object, let's make it work. It was based on doing, taking advantage of broadcast FM stations. One thing that people, to kind of back up for a second, what they like about FM is that the signals they're all over the place, they're all around the world, and they're fairly high power, so it's not uncommon that they're 30 kilowatts. And because of the frequency range, they actually have good propagation characteristics. So you can see things in the conventional case, you get line of sight to the horizon. So depending on how high up you are interested, you can see a long way, hundreds of kilometers. And then the second one I'll talk about in just a minute is this Monostache Ridge radar. That's the total low-cost system that is really kind of inspiring, but they take advantage of a relatively unique feature that the rest of us don't have. So here's the Lockheed Silent Sentry. They sell this thing for like on the order of $1 million. You know you're in trouble when this rack to the left is full of all this very expensive HP test equipment over here. This thing fits, they've got a fixed installation, they have the mobile installation. The mobile installation kind of comes in a container, and then it has these, their phased array antennas down the side of the container. So I think they use the container body itself as actually the screen behind it, and then they've got the antennas vertically, dipoles across it. So we figure, well, hey, let's see what we can do. If they do it for $1 million, can we get it for 1,000th of that, say? This system was the one that was really the most inspirational to me because these guys at University of Washington, they did something very simple. I mean, they score major points in the hacking universe, is that the university is located in Seattle, but the university also has an astronomical observatory about 150 kilometers away. But there's this mountain range between the university and the astronomical observatory. So what they do is they have one antenna that's just hanging out the window of the EE department, and it sees the transmitter that's right over there, the rock and roll radio station, FM station. Again, it's about 100 megahertz. And then they have another antenna. This is a YAGI, directional antenna at the observatory that's pointed north. What they're interested in is ionospheric phenomenon. They really want to know about plasma, aurora borealis, this kind of stuff. There are people who really care about this stuff, and these are some of them. I mean, it's cool. I mean, they get their own journals. Let me tell you, you're going to go, oh wow, there we go. And the cool part for them is that thing about how you get that coherent. You got to have that coherent sampling on both places. Is they use GPS clocks on both ends. Now, one thing I don't know that people know about GPS. Mostly we think of it as for location. But you can buy receivers that are specially tweaked up to do really good timing. So they get really good. I mean, actually there's a mailing list called Time Nuts. I don't know if you guys are familiar with this. These are for people who they have the hydrogen maser in their basement. I mean, they're out of control. But if you want to know what time it is to 1 part in 10 to the 12th, there are people out there who will tell you. So they know, they got their own little eBay, the cult of eBay, where they get the rubidiums and the cesiums. Those things aren't relatively affordable. The hydrogen maser, I guess that's really the holy grail. When you've got that, you're as good as National Standards Lab. So again, the cool thing they do on this is they got this mountain range. So this avoids the problem of how do you keep the direct path from just swamping this little tiny reflection that comes back. The other thing is, so they've got their antenna aimed up at a pretty good angle, because again, they're in Seattle and they're looking north up over Canada towards Alaska. And they see stuff moving that's 1,200 kilometers away. It's like the edge of the atmosphere slanted up. And it's pretty cool, because I've seen some of their presentations and some of the graphics they've provided, and they've got big stuff moving, say, 1,500 meters a second up there. And if you're HF amateur radio operators, basically the stuff they're mapping is the source of sporadic E propagation. So, all right. So then it comes down to, all right, what are we going to do? We want to build, we want to build a radar system. We're certainly not going to run the transmitter. That's, we just punt on that. And so we picked FM broadcast. Again, the main choice is there's a couple of existence proofs that it works, and the other thing is that with the hardware that we already have, we think we have a pretty good fit on what we can do. So the signal's about 100 megahertz. This is 3 meter wavelength. Kind of gets into why you care about stuff like that is it sizes your antennas. So there's some stuff we'll be doing later. And one of them is to build this big screen between our antennas. But you start looking at these big metal screens, and they've got to be 1.5 times their wavelength. So all of a sudden I'm thinking I have a 5 meter by 5 meter big square of mesh, and it starts to not look very portable. So, okay, there's the theoretical distance resolution you get basically is the speed of light divided by the bandwidth of interest. That gives you about 3 kilometers here. So you can kind of think about this. You're getting, how do I want to say that? Anyway, trust me, that's about the answer. There's also this other technique you can Google, follow the tips in the previous talk. On super resolution techniques, there's some great academic papers on this. And this stuff's getting applied now. All right, now back to the reality of why we picked this. We need to sample these multiple antennas coherently. And the strategy we were going to do, we're going to say, okay, what's the simplest thing that could possibly work? And that's 2 antennas, one pointed directly at the transmitter and one pointed away. So in the simplest case, we got to be able to sample 2 things at the same time, and have we care about is it one sample behind or not, or what's the phase of it? So some of you may have seen these things we've had here. This is the I got a picture of this in a minute, but I just wanted to show you this. Instead of having that rack of gear, we're going to try to do it with this thing. This is the Universal Software Radio Peripheral. And the hardware was designed by Matt Edis, who's a colleague of mine. And then this whole design is open source, and all the software is in the GNU Radio code base. So what it has is 4 A to D converters, high speed, 64 megasamples, and 4 D to A's for transmitting, FPGA, all that. Looks like that. The cool thing about this is we can do up to 4 channels. And if you look, this is about, by the time you get all the pieces you want, it's about $700 US. And the cool thing is there's nothing else out there that comes anywhere close to the performance this thing has for the price. I mean, there's lots of people that'll sell you 4-channel high-speed stuff, but they're going to be like $10,000 or more. It's sort of the same block diagram here. There's these receive daughter boards, the converters, FPGA in the middle we do some of the signal processing on the FPGA. Basically do channel selection and filtering on there. And it hooks up over the USB 2. Everything in the system is downloadable over the USB. So we load the firmware into the USB 2 controller over it, and then we use that firmware to load the contents of the FPGA. So it's completely flexible. Okay, and I wanted to talk a minute about this bandpass sampling, not like we're going to do all the math here, but just to give you